Hello, welcome to the new lecture of Math-S400 Mathematics and Economic Modeling. In today's lecture we're going to talk about the notions of convexity and then also of notion of concavity, and we're going to see what this impacts Burgess maximization theorem that you have seen during the previous lecture. So let me start by defining the notion of convexity. Okay, so let's take a set S, which is a subset of vectors, right? So it's a subset of Rk, and we're going to say that the set is convex if for any two vectors, let's call it x and y, in the set, and then for every number alpha, right, which is between 0 and 1, so alpha is in the interval 0, 1, we have that if we take alpha times x, where here x is the first vector, plus 1 minus alpha times y, then this new vector here, alpha x plus 1 minus alpha times y, is also in the set S. Okay, so it basically says if you have two vectors, and then for any number, the convex combination of these two vectors, this is what's called the convex combination of x and y, is also an S. Okay, so if I have here in the vector x and I have here the vector y, then what's this vector here? So for example, if I would plug in alpha equal to 1, then here I have 1 times x plus 0 times y, so this would be the vector x itself. Okay. On the other hand, if I would plug in alpha equal to 0, which is the other end of this interval, then I here have 0 times x, so this is 0, plus 1 times y, so I'm here having y. Okay, so you know that if alpha is equal to 1, I have the vector x. If alpha is equal to 0, I have the vector y. So what would happen if I, for example, plug in alpha equal to 1/2? Then I have 1/2 times x plus 1/2 times y, which is exactly the midpoint between x and y. Okay, and you see that if x varies between 0 and 1, then basically you going to take all the points on this line segment between y and x. Okay, so basically this definition means that if I have an x and y in the set S, then for anything, any point or any vector on the line segment between x and y, all these points also have to be in the set S. Okay, so a convex set, for example, this is here is a convex set, right? So how can you see that this is a convex set? Well, you just verify the definition. So if I would take any 2 points in the set, then everything on the line segment between these 2 points also has to be in the set. Okay, and you can visually inspect that any 2 points that I take in the set, if I draw the line segment, then any point on the line segment also should be in the set. Okay, so this is convex. Now, to give a counterexample of something that's not convex, for example, this set here, this set is not convex. So how can you see that this is not convex? Well, for example, I can take this point and this point, which is both in the set. And then if I draw the line segment, I see that there are points on this line segment, this here, right, that are not in the set, right? So it doesn't satisfy this definition. I can find an x and a y, this is x and this is y, such that something in the convex combination is not in the set. Okay, so this is not convex. Okay, so you have many different shapes that are not convex. For example, this set would be convex, but if, for example, I cut out this piece here, then again, this here is not convex, right? Because I can, for example, find a point here and here, and then this line segment contains points that are not in the set. Okay. Another example of maybe a convex set is if you take a finitely many points, and then you join these points by line segments. Let me draw a point here, right? Then this set here, this is called a polytope, right? This is also a convex, right? Take any 2 points in the set, draw the line segment, and this line segment will also be in the set. Okay, so a set, convex set, doesn't not need to be closed. For example, I can have this open ball, right? So it's everything inside the ball, but not on the boundary. Then again, if I take 2 points in the set, right, they cannot be on the boundary. If I take the line segment, everything will be inside the set. Okay, so this is also convex. Okay, so this is the definition of a convex set. It's an important definition. So we're going to use the definition of a convex set in order to define the notion of a convex function. So let me take a function f that goes from some set, let me call the, maybe not s, but let me call the domain, right? So it's the domain of a function, and it goes to the real line. And for the simplicity, I will require D to be a convex set. Okay, then what we can do is we can look at a set of points which we call the epigraph of f. So this it's called the epigraph. So what's this? These are pairs of vectors numbers, right? So we take a vector in the domain and we take a number y and r, right? So this is in the domain times r. So basically it says something in D and then something in the range, such that y is greater or equal to f of x. Okay, so this is called the epigraph, and maybe I should draw it to make it clear how the set looks like. So for example, here I have a function. Okay, so this is my function f. So I'm looking at points x in the domain. So this is here the domain, and y is in r, right? So it's basically in x and r. So it's a point on the plane here, such that y is greater or equal to f of x. So for example, here, if this is my x, all the y's that are greater or equal to f of x, so this is f of x. So this isn't this entire line segment here that goes up to infinity. Every point on this line segment will be in the epigraph of f. And I do this for every x in the domain. Okay, so the set that I will get in the end is going to consist of everything that's above the function f. So this is this arched set here. This is the epigraph of my function f. Okay, so now we have the following definition. We say that the function f from the domain to R is convex if this set, epigraph of f, is a convex set in D times in this region. Okay, convex subset of this. Now here, this convex here, this is the definition of this convex. This relates to the function. This definition of convex here relates to the fact that this set here is convex. All right, so this is convexity as you have seen before in terms of a set, right? In terms of this, like this set here. This convexity is a definition that we state here is when a function is convex. So we use the same words, but basically there are two different things, right? This is convexity of a function, and this relates to convexity of the set. So let's write this out in detail. So we have the epigraph of f has to be a convex set, right? So this means that if I take two elements that are in the epigraph, right, then anything on the line segment between these 2 points should also be in the epigraph. Okay, so here we see, for example, that this is not the case. If I would take this point here, this is in the epigraph, and I would take this point here, which is in the epigraph, then there are things on this line segment, okay, that are not in the epigraph, right, because they fall below the function. Okay, so clearly this is not a convex function. So if I would draw a convex function, it would have to look like something like this, because if I take 2 points here that are above the function, right, in the epigraph, then anything on the line segment between these 2 points should also be above the function. Okay, so if I just translate this notion of a convex set, what it means that if let's call it x1 and y1 are in the epigraph of F, and then I have x2, y2 in the epigraph of F, and for all alpha in 0, 1, I have that convex combination of these two, right? So alpha x1 y1 plus 1 minus alpha x2 y2 is also in the epigraph of F. Okay, so let's write this out in terms of the definition of the epigraph. Okay, so here this means that y1 greater or equal to f of x1. Okay, so this is the definition of the epigraph. This is in the epigraph if y1 is greater or equal to f of x1, and if I have a y2 greater or equal to f of x2, then for all alpha between 0 and 1, this should be in the epigraph. So what's this here? Right, this is the same as the vector or the pair. So I can take the alpha inside, right? This is like a stacked vector, a vector and a number. So this is alpha x1 plus 1 minus alpha x2, and then the second component is alpha y1 plus 1 minus alpha y2, right? So this here is the same as this here, right? So if I look, when is this in the epigraph? Well, if this number here is greater or equal to f of this number here, of this vector here. Okay, so for all alpha I should have that alpha y1 plus 1 minus alpha y2 is greater or equal to f of alpha x1 plus 1 minus alpha x2. Okay, so let me make the picture again. Here I have my convex function. I have a y1 greater, so I have an x1 and an x2. I have a y1 greater than f of x1. So for example here, this is my y1. I have a y2 greater or equal to f of x2. So for example, it's this one here. Then alpha y1 plus 1 minus alpha y2. Right, so in particular this is y1. This should be my y2. Then alpha y1 plus 1 minus alpha y2 should be somewhere between these two. And then alpha x1 plus 1 minus alpha x2 should be on the line segment between these two. Right, and then I have that this point here, if I draw it correctly, right, should be above the function f. Right, so here, this point here, this here is f of alpha x1 plus 1 minus alpha x2, right, and this point here is alpha y1 plus 1 minus alpha y2. Okay, so you see that this should be greater or equal to this thing here, right? So that's basically the translation of this definition of convexity towards the function values. So there's one particular case which might be of interest here, and this is when these two inequalities are in fact equalities. Okay, so what happens then? Well, in this case, let's say that y1 is equal to f of x1 and y2 is equal to f of x2. Well, it satisfies this definition, right? If it's equal, then it's also greater or equal. right? So in this case, you also have that for all alpha in between 0 and 1. This inequality should be satisfied, right? So we have alpha times y1, but now y1 is equal to f of x1. So we can simply write f of x1 plus 1 minus alpha y2, but y2 is equal to f of x2. So we can simply write f of x2, right? This is greater or equal to f of alpha x1 plus 1 minus alpha of x2. Okay, so the convex combination of the function values is greater or equal to f of the convex combination in the domain. And this is probably a definition of convexity that you might be familiar with, right? F alpha x1 plus 1 minus alpha x2 is less or equal to alpha f x1 plus 1 minus alpha f of x2. And in fact, you can show that this definition here and this definition here, right, these are equivalent definitions, right? So either you can use this definition or you can use this definition. So we already have shown that this implies this, right? In order to show that this implies this is quite an easy exercise. So you use this here to start with, then you can show that this is greater or equal to this, right? By the fact that this is greater or equal, y1 is greater or equal to f of x1 and y2 is greater or equal to f of x2. We can show that alpha y1 plus 1 minus alpha y2 is greater or equal to alpha f of x1 plus 1 minus alpha f of x2. Then this will be greater than this, right, by assumption. So we have that this is greater or equal to this, right? So we can show that this is an if and only if statement. So there are several equivalent definitions of convexity of a function. Either you say that the epigraph is a convex set, or you can use this definition, or you can use this definition. Okay. So there's a related condition that's not called convexity of a function, but concavity. And for concavity, so we have a function that's from some domain to R, and again you assume that the domain is convex, right? So instead of the epigraph, you look at something else that's called the hypograph of f. So again, it's a combination of something in the domain and the number, right? So it's in D times R. And now we don't have that y is greater or equal to f of x, but y is less or equal to f of x. Okay, so if I draw it, it's just the reverse of the hypograph was everything above. The epigraph was everything above. The hypograph is all points that are below the function. Okay, and then we say that f is concave, right? This is the definition. F is concave if hypo f is convex set in D times R. Okay, so again we define concavity of a function as the property of a set being convex. Okay, so how does it look like? Concave functions look like this. So if I take any 2 points in the hypograph, then everything on the line segment between these 2 points should also be below the function. Okay, and if I write this down in terms of as you did before for convexity, right? So you can use this definition, but so some things change, and in particular what changes are the inequalities, right? So in particular, if I take a y1 lower or equal to f of x1, and if I take a y2 lower or equal to f of x2, then I need that for all alpha between 0 and 1, alpha y1 plus 1 minus alpha y2 is less or equal to f of alpha x1 plus 1 minus alpha x2. Okay, so if this is the case, then this follows. So that's the definition of equivalent definition of concavity. And as we did for convexity, we can take the special case where y1 is equal to f of x1 and y2 is equal to f of x2. And then we have the definition that for all alpha between 0 and 1, alpha f of x1 plus 1 minus alpha f of x2 is lower or equal to f of alpha x1 plus 1 minus alpha x2. Okay, so this is the first condition definition. You can call this a second definition of concavity, and this is the third definition of concavity, right? And you can show that all of these three definitions are equivalent to each other. All right, so let's recall the definition of convexity, and I will just write down one of them. So for all alpha between 0 and 1, alpha f of x plus 1 minus alpha f of x2, we call this x1. So convexity, right, is greater or equal to f of alpha x1 plus 1 minus alpha x2. Okay, so this is the definition of convexity. Now there exists a notion that's called strict convexity, and so you have that f is strict convex. So what do we need? We need, first of all, for all x1, x2 in the domain, and for all alpha, this property holds, right? So basically it's convexity. And then we need a second requirement in addition. That's for all x1, x2 in the domain, and for all alpha strictly between 0 and 1. So here we exclude 0 and 1, right? So here 0 and 1 were part of this interval. Here we exclude the 2. Then if x1 is different from x2, it follows that alpha f of x1 plus 1 minus alpha f of x2 is strictly bigger than f of alpha x1 plus 1 minus alpha x2. Okay, so that's the notion of strict convexity. So in order to show the difference between the two, so for example, this function here is convex, right? So if I take any 2 points in the epigraph, anything on the line segment between the two is also in the epigraph. But now I can show, for example, that this function here, that has this flat portion at the bottom, let's say, this is not strictly convex. So how can you see that it's not strictly convex, right? So I can take 2 points x1 and x2, for example this one here, x1 and x2, and I can take an alpha between 0 and 1, right? So it's strictly between the two. So this could, for example, be alpha x1 plus 1 minus alpha x2, right? Then I need that alpha f of x1 plus 1 minus alpha f of x2, right? So this is f of x1, this is f of x2. So alpha f of x1 plus 1 minus alpha f of x2 will be here, right, on the line segment between the two. Should be strictly bigger than f of this point, which is exactly the same point, right? So this is not strictly convex because this green point is not strictly above the function value, but basically it's on the function value. Okay. So in order to have something that's strictly convex, we cannot have flat portions of the function. So we need a shape that has curvature at every point, right? So we cannot have flat portions. So in this case, if we take an x1 and if we take an x2, if you take alpha alpha f of x1 plus 1 minus alpha f of x2, we get at this point f of alpha x1 plus 1 minus alpha x2 will be this point, right? So we see that this point is strictly bigger than this point, so this is strictly convex. Okay, and then you have the related notion of strict concavity. Okay, so what needs to be changed is very little. So here, instead of convexity, we assume concavity. So basically the only thing that you need to change is the inequality sign here. And then this remains the same. The only thing that we have to change here is make this a strict inequality here, right? So basically convexity and concavity are very related. You only have to flip some inequality signs. Okay, so this is the notion of strict convexity and strict concavity. Okay, so we have seen convexity, we have seen concavity. Now we're going to see something that's called quasi-convexity. So instead of the epigraph, now we use a different kind of graph, right? So let's take beta to be a number r, and now we're going to look at the upper level sets of f at beta. Let me call this f at beta. So what's this? This is a subset of the domain, right? So it only contains elements in the domain such that f of x is greater or equal to beta. All right, so for any beta you have a set like this, right? So we have seen that the epigraph only is one set, right? For a given function it's only one set, but here we have a set for every possible beta that you can think of. Okay, so for example, if I have let me draw a function like this. Okay, so let me take beta to be this one. So I need all the x's in the domain that are greater or equal to beta, right? So here the upper level sets of f at beta will be the entire domain, right? Because for every x, f of x is greater or equal to beta. If I take the beta here, right? So for example, let this be my domain, right? So I have, let me put some bounds here. So if this by beta, I look at all the x's that have a value greater or equal to beta. So this is my beta here. So which x's have a value f of x greater or equal to the beta? Well, every point here, f of x is greater or equal to beta, then not the points here, then again the points that I have here. Right, so basically it's this entire region here, and then this entire region here. Okay, this is what I have. I can increase my beta even further, right? Then I have beta here. Okay, so what are all the x's in my domain for which f of x is greater or equal to beta? Well, here it's below, and then I start in my domain here, all these values, f of x is greater or equal to beta, then not here, and then here I start again. Okay, and so on and so on. And I can do this for example, if I take a beta here, then the upper level sets of f at beta will be the empty set, right? Nothing, there's no x in the domain that has a function value that's greater or equal to beta. So these are upper level sets, and then I have lower level sets. Let's call this lower level LL of f at beta, and this is very similar. It should be equality sign. It's everything in the domain such that f of x is less or equal to beta. Okay, So for example, if I try to draw the same function, so here I have my domain. So what are all the x's such that f of x is lower or equal to beta? So here I have beta. So here, for this value of beta, my lower level set is equal to the domain. Okay, so because all the function values, no, I made a mistake, right? I look at all the function values that are less or equal to beta, so here I have the empty set, right? Sorry for the mistake. Okay. If I raise my beta, I look at all the x's, here fx is bigger than beta, bigger than beta, bigger than beta. Here I start, that's for this entire interval, f of x is greater or equal to, is lower or equal to beta, and then here I have to stop again, so it's this entire interval here. If I take my beta somewhat higher, I draw the line here. So here I have all these values x here, and then I have all the values x in this interval, and then again not here. And if I look at very high betas, then basically everything in the domain will have a function value below beta, right? So basically they're the mirror images of this thing here. Okay. So for example, let me look at convex function. Okay. And let me look at the lower level sets. Okay, so if I draw a beta, so I need to find all the x's in the domain such that f of x is lower or equal to beta. Okay, so here in this case, these are all the x's that satisfies this. And you can see that this is an interval here, right? So in particular, this is a convex set, right? If I take two x's for which f of x is below beta, then any point on the line segment between the two will also be below beta. And I can do this for every beta, right? And if this function is convex, then this will also always be an interval, right? So in this case, we say that if f is convex, then the lower level sets are convex. Okay. So in particular, what does it mean for these sets to be convex? Well, it means that if I take two elements in the set, then the convex combination should also be in the set, right? So if I take an x1 and an x2 in the set, which means that f of x1 is lower or equal to beta and f of x2 is lower or equal to beta, then for all alpha between 0 and 1, f of the convex combination alpha x1 plus 1 minus alpha x2 is also lower or equal to beta. Okay, and here I have hinted already that convex functions satisfy this definition. Okay, so why would convex functions satisfy this definition? Well, if f is convex, what do we know? Well, we know that f of alpha x1 plus 1 minus alpha x2 is lower or equal to alpha f of x1 plus 1 minus alpha f of x2, and both are smaller or equal to beta, right? So this is lower or equal to alpha beta plus 1 minus alpha beta, which is equal to beta, right? So if f is convex, then this definition here, or this condition here, is always satisfied. Okay. However, the reverse is not necessarily the case, right? So let me draw a picture So here I have my domain. So here I have a function f, right? So it curves like this, and then it curves to up, and then it curves the other way. Okay, and you can see that for every beta that I draw, you can look at all the values of x for which f of x is bigger, lower or equal to this beta, and you would see that it's convex set, right? So all these things are intervals, so they're all convex sets, right? So this f here, you have that lower level sets of f at beta are convex. On the other hand, f is not convex. Okay, so how can you see this? For example, if I take this point here, and if I take this point here, both are in the epigraph, right? They're above the function. But if I draw the line segments, then there are points on the line segments that are not in the epigraph, right? So this is not a convex function. However, all the lower level sets are convex. So we need a different notion in order to generate this property, right? So this is going to be the definition. So we say that f is quasi-convex if for all beta in R, the lower level sets of f beta is a convex set in the domain. Okay, and then we can define a similar thing. You can say that f is quasi-concave. Now we're not looking at lower level sets, but we're looking at the upper level sets. F of beta is a convex set, right? So in order to see a function that's quasi-concave but not concave, for example, this is also a nice quasi-concave function, right? So how can you see that it's quasi-concave? If I take any beta, right, it has to hold for every beta. But if I look at all the x's, such that f of x is greater or equal to beta, here I get this value of x, and I see that this is a convex set, right? However, it's not concave because I can take 2 points, for example, the point here and the point here, and then there are things on this line segment which are not in the hypergraph, right? They're not below the function. So this here, this function, is a quasi-concave but not concave, and this one here is a quasi-convex but not convex. However, you can show that every concave function is quasi-concave, but the reverse is not true, right? So quasi-concavity is a generalization of concavity. Okay. So we already have seen that quasi-convexity is that lower level sets are convex. So basically, if I adjust this definition, it means that for all x1, x2 in the domain, for all beta in R, if f of x1 is lower or equal to beta, f of x2 is lower or equal to beta, then for all alpha n 0, 1, this has to hold. Okay. Quasi-concavity, you can use a similar, so this is the definition of quasi-convexity. For quasi-concavity, you have a similar definition. F is quasi-concave if for all x1, x2 in the domain, and for all beta in R, if f of x1 greater or equal to beta, f of x2 greater or equal to beta, then I have that for all alpha between 0 and 1, f of alpha x1 plus 1 minus alpha x2 should also be greater or equal to beta. Okay, so this is the definition of quasi-concavity. Let me for convexity, so we just change these inequality signs and these inequality signs. Okay, so this is just a restatement of the fact that the upper level sets are convex. So in general, I can put my beta to be equal to f of x1 or f of x2, right? So if I look at the definition of quasi-concavity, I can put beta to be equal to, so it has to be lower than f of x1, it has to be lower than f of x2. So I can put it equal to the minimum of f of x1, f of x2, right? If it's equal to the minimum, then it satisfies both of these conditions. Okay, so if I do this, what do I get here? Well, I get that for all alpha between 0 and 1, f of alpha x1 plus 1 minus alpha x2 is greater or equal to the minimum of f of x1, f of x2. Okay, so basically I'm just putting here beta equal to the minimum of both. Then if I plug in beta here, I get this condition. Okay, and in fact you can show that this definition here and this definition here are identical. Okay, so how can you see this? Well, let's take an f of x1 greater or equal to beta, f of x2 greater or equal to beta. Then I know that beta is lower or equal to the minimum of these two. Okay, so I know that beta is lower or equal to this, and this is lower or equal to this, so beta will be lower or equal to this here too, right? So this gives you the arrow from the bottom to the top. Okay, so these two conditions are the same, right? So we have three definitions of quasi-concavity. The first says that the upper level sets are convex. The second one is this definition here. And then the third one is this definition here. And you can use whichever one you want. They're all three of them are equivalent definitions. Okay, so we also have a strict version of quasi-concavity and quasi-convexity. So we say that a function is strictly quasi-concave. So what we need, so first we need the definition of quasi-concavity, right? So this means that for all alpha between 0 and for all x1, x2, this inequality holds, right? This is what you have seen previously. So this is the first thing that has to hold, and then we have somehow a stricter notion, which means that for all alpha strictly between 0 and 1, and for all x1, x2 in the domain, if x1 is different from x2, then I have this inequality, but then with a strict sign. So alpha x1 plus 1 minus alpha x2 is strictly bigger than the minimum of f of x1, f of x2. Okay, so in order to draw your function that's quasi-concave but not strictly quasi-concave, so for example this function here, so for example this flat portion here does not satisfy the strict part. So how can you see this? You can have an x1 here, an x1, 2 here. F of x1 and f of x2 are identical, right? So this is a horizontal part, so the minimum is equal to both. But then f of alpha x1 plus 1 minus alpha x2 is also on this line segment, right? So it doesn't satisfy the strict inequality. Okay, and for this kind of function, right, you immediately see that any strict quasi-concave should have a peak somewhere, right? So you cannot have flat portions at the top. Okay. So for quasi-convexity, you have a very similar thing as for quasi-concavity, right? Which I have explained just a minute ago. So this is the definition of quasi-convexity. But now, for the special case, you don't take beta to be equal to the minimum of the two, right? But beta is greater or equal to fx1, beta is greater or equal to fx2. So what you do is you set beta to be equal to the maximum of fx1, fx2, right? And then you can show that quasi-convexity has an equivalent definition, and it says that for all alpha between 0 and 1, and for all x1, x2 in the domain, f of alpha x1 plus 1 minus alpha x2 is less or equal to the maximum of f of x1, f of x2. Okay, and then you also had the notion of a strict quasi-convexity, and then this requires that this property holds, and in addition for all alpha strictly between 0 and 1, and for all x1, x2 that are distinct, then this holds with the strict inequality. Alright, so for every concavity notion you have an opposite convexity notion, and for every strict quasi-concavity notion you have a strict opposite strict convexity notion. Right, so all these two are very similar to each other, and you can read the definitions and details in the lecture notes. So in order to give an example of a quasi-concave function, so normally we assume that utility functions are quasi-concave, right? So take a utility function u that goes the domain could be something like rk plus. These are all k-dimensional bundles, and it produces a number r. Okay, so for quasi-concavity, what we need to do is we need to look at the upper level sets of the utility function u at some particular beta. Right, so these are all the bundles in rk plus such that the utility of q is greater or equal to some number beta. Okay, so in economics these are also called the upper contour sets of the utility function. So remember from your micro course, if you have, for example, two goods, q1 and q2, what you can do is you can draw the indifference curve of this utility function. So for example, these points here on this line, these are all the bundles q1, q2, such that u of q1, q2 is equal to some fixed number, let's call it beta, right? So then this is the indifference curve for level beta. So what now are all the bundles that give utility greater or equal to beta? Well, it's simply every point or all the bundles that are above this indifference curve. Okay, so what does quasi-concavity requires? It requires that this set here is a convex set. Okay, so in particular, if I take two bundles above the indifference curve, then any point on the line segment between these two bundles is also above the indifference curve. Okay, and this is what you normally say, that if indifference curves are convex, right, then the utility function will be quasi-concave. Okay, so this is the notion of why quasi-concavity is so important for utility functions, because they give these nice convex shaped indifference curves. So before we state a theorem in this lecture, I need to define one notion. So the notion is of a convex valued correspondence. So let me take a G, which is a correspondence that goes from some domain to some range, something like this. Okay, so for example, if I draw G, it might be something like this. Okay, so we have the domain here and then the range on the y-axis. So we say that G is convex valued if for all x in the domain G of x, right? So you know that G of x is a subset of R, okay, because its correspondence is this thing is a convex set in the range. Okay, so we know G of x is a subset of R. If it's a convex set, then we say that G is convex valued. Okay, so for example, for this case here, for any x in the domain that I take, I make G of x. So here it's this interval here. So this interval has to be a convex set, which is clearly the case here. Okay. Not every correspondence is convex valued. So for example, if I would have a situation where I have a gap in the correspondence here, right? So this part here is not part of the correspondence. Then for example, for this particular x, I look at G of x, which is this portion plus this portion, and you see that this is not a convex valued, right? Because I can take a point here, I can take a point here, and then there are elements on the line segment between the two that are not in correspondence. Okay, as another counter example, for example, if I have this is my correspondence, okay, then for example at this point here, my G of x are these 2 points, and this is clearly not a convex set, right? So in order to make it convex valued, what I need to do is I need to include every point between these 2 points here, and now it's convex valued. Okay, so in order to know that G is convex valued, basically for every x in the domain, this set here, G of x, has to be a convex set. Note that, for example, here the graph of G is not convex, right? So I can take a point here and a point here, and then there are things on the line segment that are not in the graph. However, this doesn't mean that G is not convex valued, right? So for convex valuedness, you fix the x and you only look at G of x. If this is convex, then it's enough to be convex valued. Okay, good. Okay, so let's now return to Burgess maximization theorem. So remember, what did we have? We wanted to maximize a function f that depends on a decision variable, right? So we want to maximize with respect to x, and it may depend on a set of parameters, theta, and subject to x and g of theta. Okay, this was our constraint, and we had that f was a function that went from some domain, let's call it x, and takes a theta in some set theta, and it gives you a number, right? And we assume that f is continuous. Okay, that was the first thing. And then we had that the correspondence G takes some theta, gives a subset of the domain X, and we assume that G was upper hemicontinuous and lower hemicontinuous, right? So it's both. And in this case, we have seen Burgess maximization theorem to say that if we can solve this maximization problem, and what we get out of it is a function that depends on theta, okay, and this will be continuous. And in addition, we can get the solution correspondence, gamma of theta, which are simply all the x's in that are feasible, right? So they satisfy the restriction such that f of x theta was optimal g of theta, right? So this all the x's that are feasible that give you the optimal solution. And then you say that this is upper Hemi continuous. So now we're going to impose some convexity concavity restrictions, and you will see how this impacts this result. So what are we going to assume? We're going to assume in addition that f is quasi-concave, right? So for example, it's a utility function, right? We have seen that normally utility functions are quasi-concave. And then we're going to assume that G is convex valued, right? So for any theta, G of theta is a convex set in X. Okay. Well, if these two conditions are satisfied, then we can show, and this is what we can show, that gamma is also convex valued. Okay, so that's the first thing that we're going to show. And then the second thing that we're going to show is the following. If f is strictly quasi-concave and G is convex valued, well, in this case we're going to show that gamma is single valued. So what does it mean for gamma to be single valued? Well, it means that for every theta, this set here only contains one element. Okay, there cannot be two optimal elements. This also means that if I solve this maximization problem, then for any theta I will get a unique solution, right? There will be only one x that solves this problem. Okay, so let's go to the proof, and first let us show one. Right, so we assume that f is quasi-concave and G is convex valued, and we need to show that gamma is convex valued. So what do we need to show? Well, we need to show that for all theta in the domain, gamma of theta is a convex set. Okay, so how do we show that this is a convex set? Well, we take two elements out of the set, we take the convex combination, and then we have to show that the convex combination is also in the set. Right, so we need to show that for all x1 and x2 in gamma of theta, and for all alpha between 0 and 1, alpha x1 plus 1 minus alpha x2 is in gamma of theta. Okay, so let's do this. Let's take, let x1, x2 in gamma of theta. Okay, so let's look at the definition of gamma of theta. What do we have? Well, we have that x1 is in g of theta. We have x2 is in g of theta. We have f of x1 theta to be equal to v of theta, and we have that f of x2 theta is equal to v of theta. Okay, so these are all the things that we have. So let's take an alpha between 0 and 1. So we can take alpha x1 plus 1 minus alpha x2. And because x1 is in g of theta, x2 is in g of theta, and remember g was assumed to be convex valued, we know that this here is also in g of theta, right? So this vector, alpha x1 plus 1 minus alpha x2, is feasible, so it satisfies this this restriction of the maximization problem. Okay. So in addition, what do we also have? We have that f of f is a quasi-concave function. So f of alpha x1 plus 1 minus alpha x2 is greater or equal to the minimum of f of x1, f of x2. Okay, so this follows from quasi-concavity of the function f. Okay, however, we know that the first here is equal to v of theta, and the second one is equal to v of theta, so we know that this is equal to v of theta. Alright, so what do we have? We have that this vector here was feasible, and f, I forgot to add the number theta here into the f value. F of this number here for this theta is greater or equal to v of theta, right? So it's feasible and it's bigger than the optimal solution that I can get. So in this case, I know because the value is bigger than whatever I can get, it has to be equal to v of theta. So alpha x1 plus 1 minus alpha x2 is in gamma of theta. Okay, so I forgot to specify here what I mean if f is quasi-concave. I mean is quasi-concave in x, right? And here strictly quasi-concave, I mean strictly quasi-concave in x, right? So this means keeping theta fixed, right? It's a quasi-concave function of x for a given theta. Okay, sorry, I wasn't super clear about this. Okay, so you see we have taken two optimal solutions. Then the convex combination of these solutions is also feasible, right? Satisfies the constraint, and f of this convex combination has to have a value that's greater or equal to the optimal value here, so it has to be an optimal solution also. So this is proofs point 1. And now for point 2, we assume that f is strictly quasi-concave in addition to convex valuedness. And then you have to show that gamma is single valued. So how are we going to do this? We're going to do it by proof by contradiction. So if you have to show that a solution is unique, normally you use the proof by contradiction. You assume that it's not unique, and then you derive a contradiction. So assume that gamma of theta is not single valued, right? So if it's not single valued, then it means that it has at least two elements. So let x1 and x2 be in gamma of theta, and x1 different from x2. Okay, there are two elements and they're different. Okay, so we know that x1 is in g of theta, x2 is in g of theta, and we know that they're optimal, so f of x1 theta is equal to v of theta, f x2 of theta is equal to v of theta, right? So this is simply by definition of the correspondence gamma here. And now we can use the same trick, right? So we can take an alpha between 0 and 1, but now we're going to use strict quasi-concavity, so we're going to take an alpha strictly between 0 and 1. Okay, so alpha x1 plus 1 minus alpha x2 will now also be in g of theta, right? This because g of theta is convex, right? Because g is a convex valued correspondence. And now we can use strict quasi-concavity of f to show that f of alpha x1 plus 1 minus alpha x2 theta is strictly bigger than the minimum of f of x1 theta f of x2 theta. And I see that here I have also forgot the thetas. Okay, again both are equal to v, so the minimum is equal to v of theta. So what have we done here? Here we have found a solution that's feasible, right? We have something in the domain that's feasible, and f of this something that's feasible is strictly bigger than what's optimal. Of course, what's optimal is the best whatever I can find in this correspondence. So it's impossible that something is bigger than what's optimal. All right, so this gives you a contradiction. And the contradiction then shows that this here is impossible, so they have to be the same. So indeed, gamma is single valued. So remember what we looked at in the previous lecture. We looked at maximizing a utility function subject to Q is in B is in the budget set, right? And recall the budget set was equal to all the bundles Q in RK plus, such that P times Q is lower or equal to M. Okay, so let's first show that this is convex valued. So what do? We take two bundles Q1 and Q2 in BPM, and then you have to show that alpha Q1 plus 1 minus alpha Q2, so for all alpha between 0 and 1, they're also in the budget set, right? So for every price and income, this set has to be convex. So this is quite easy. If Q1 and Q2 are here, then we have that Q1 is greater or equal to 0, Q2 is greater or equal to 0, PQ1 is lower or equal to M, PQ2 is lower or equal to M, right? So if both are greater or equal to 0, then of course alpha Q1 plus 1 minus alpha Q2 is also greater or equal to 0. And here we have two inequalities, so we can take the convex combination. So we have P alpha PQ1 plus 1 minus alpha PQ2. These are all dot products. Is lower or equal to M. Here this can be rewritten. We can take the dot product of alpha Q1 plus 1 minus alpha Q2. So this is the same inequality, right? So we have seen that this bundle here is greater or equal to 0, and P times this bundle is lower or equal to M. So these two conditions show that alpha Q1 plus 1 minus alpha Q2 is in the budget set. Okay, so this shows that B is indeed convex valued. Okay, so from this we derive the indirect utility function, and we derive the demand correspondence, right? All the optimal utility maximizing bundles. So now we can show that because this here is a convex valued correspondence, we can show that if U is quasi-concave, then gamma PM is convex valued. Okay, so if you have two bundles that are optimal, then the convex combination of these two bundles will also be optimal. This is basically what it says. Okay, and then if U is strictly quasi-concave, well, from this it follows that gamma PM is single valued. So in a sense, if I solve this utility maximizing problem, I will only have a unique optimal solution, right? There's only one Q that solves my problem for every P and M. So if then this is equal to this optimal bundle, well, basically what we have then is, because this is upper hemicontinuous, we have seen in one of the exercises on correspondences, if you have an upper hemicontinuous correspondence and a single valued, then basically what this depicts, so for every thing in the domain you only have one value, right? So the curve that you get out of it has to be a continuous function. Okay, so basically this optimal solution then defines a Q for every P and M. Right, for every P and M you have a unique bundle, so this will then be the demand function. Right, it's not the correspondence anymore. It's impossible that two bundles maximize the same utility maximization problem. There's only one bundle, and this is the unique bundle. So this is called the demand function. It's no longer a correspondence. Okay.